Good morning and happy Monday. On Friday, we finished a short wastewater unit. And as I mentioned when we talked briefly about tertiary treatment, that what we would be talking about really for the rest of the semester are a number of treatment technologies that are applied both in water treatment for actually processing, for water for both drinking water, also for industrial processing, but also these same processes are used in wastewater treatment. So adsorption, so we talk about adsorption, and we also talk about absorption. And we need to be able to distinguish between these two. Right now, we are talking about adsorption, and think of this as a surface process. So for instance, if you have air and you have contaminants in that air, those contaminants can adsorb onto a surface. You can think of that as a situation where if you happen to have someone over the house, there's smoking, and you smell the cigarette smoke long after they leave. Why? Because those chemicals from the cigarette smoke have adsorbed to, for instance, the fiber of curtains or the fibers in a carpet. Same thing is we can have contaminants in water, and those contaminants can adsorb also onto a surface. When we talk about absorption, we're talking about, think of this as a three-dimensional process. So for instance, we can think about this as a raindrop. We have CO2 in the atmosphere. That CO2 can dissolve to form aqueous CO2. So typically we're looking at Henry's law. We've talked about disinfection, where we have chlorine gas, and that chlorine gas dissolves to form aqueous chlorine. Or we can have ozone in the gas phase, and that dissolves to form aqueous ozone. So think of adsorption as a surface process. Think of absorption as a partitioning into a phase, like water. Now, let's look at this as an example. So let's start out thinking we have this situation where we have 1 liter of solution. And that solution contains a copper concentration of 100 milligrams per liter. Now we add 5 grams of activated carbon. And we allow this suspension to mix, reach equilibrium, and once it reaches equilibrium, we have 2 milligrams per liter of copper in solution. So mix this system, and it has reached solution. So what we have, think of this is our activated carbon. This is the activated carbon particles. And now, after a period of time, we have copper associated or sorbed onto that solid surface. The solid surface is the adsorbent. Okay, so this is the solid. The adsorbate is the chemical that is being sorbed. So in this case, it's copper. We also talk about a specific surface area And the specific surface area, for instance, is meters squared per gram of solid. So it's the surface area of the solid surface. And we'll talk more about the importance of that. So in this case, what we've added, is we've added 100 milligrams per liter. We have a 1 liter solution. So we have 100 milligrams that we've started with. We had 2 milligrams in that 1 liter of solution. And we added 5 grams of activated carbon. So what we have sorbed is about 19.6 milligrams of copper per gram of activated carbon. So that is the amount that is sorbed onto this carbon. So we'll use these concepts throughout this unit. Now, the forces that hold these chemicals to the surface are both physical and chemical. So if we're talking about what we call physisorption, these are weak forces, like van der Waals forces. They can be weak electrostatic forces. The delta G is about 4 to 40 kilojoules per mole. These tend to be reversible. Chemisorption is a stronger sorption. And here we're talking about covalent or ionic bonding, and you can see that the delta G is much higher than the delta G here for physisorption. And these often tend to be irreversible. We also talk about, we sometimes use the term fugacity. So fugacity is the tendency of a chemical, it actually means to flee, to want to leave a solution. So for instance, with chemicals like the polychlorinated biphenyls that we used extensively back in the 70s in everything from carbon paper to transformer fluids, those PCBs are extremely insoluble. And if we have a water containing PCBs, those PCBs tend to want to leave the water, and they'll actually attach even to the surfaces of the vessel that it's in. So these tend to be nonpolar, insoluble chemicals. On the other hand, the PFAS chemicals, the poly and perfluorinated substances, there's somewhere over about 5,000 of these. These tend to be highly variable in properties, but they're much more soluble than the PCBs. So for instance, if we're looking at sorption, it's much easier to remove PCBs with a sorption process than it is many of the PFAS chemicals. Now, if we're looking at sorption, we can look at sorption in natural systems. And the shown here is with PCBs. Hudson River in New York has extensive contamination with PCBs. The Tittabawassee River near Midland also is contaminated. The sediments are contaminated with PCBs. So what's happened over time is the PCBs in the water, where we had PCBs in the water, those PCBs have settled or sorbed onto particles. Those particles settle to the sediments, and now you have sediments that are contaminated with PCBs. Those sediments can be re-entrained. So if we have mixing here, those sediments can be re-entrained, releasing PCBs back into the environment. If you have microorganisms that are what we call benthic organisms, they live in the sediments, those can help reintroduce PCBs. So what you see here is what's actually done is put a cap. So they've dredged out the sediments that were contaminated, and in some cases they put a cap on that area to try and prevent re-entrainment of particles. We also have are concerned with sorption of various different chemicals, both organic and inorganic, onto particulate matter in the air. So you burn, you combust gasoline, you produce particulate matter, and that particulate matter can contain high concentrations of metals, high concentrations of organics. Those of you that have in 480, that look where we looked at the policy statement on the use of commercial grade fireworks. One of the concerns there are these fireworks produce particulate matter. There's all sorts of metals that are in the fireworks, give the fireworks the pretty colors, and then you have those metals absorbed onto the particulate matter. That particulate matter you breathe, you're also breathing in the metals. The particulate matter settles to the ground surface and then contaminates the ground surface. The other issue has to do with biosolids. Mike Ellis showed this image here from Eagle. What I wanted to kind of, again, show this is, for instance, if you have a industry that is releasing wastewater to the wastewater treatment plant, and those PCBs, or the wastewater contains PCBs, you can end up with PCBs in the biosolids. Well, the biosolids can be disposed of in a landfill, but those biosolids can also be just land applied onto agricultural land, in which case there's concern then about PFAS contamination of these soils, and then the potential for some of that PFAS chemicals to end up in the food, some of it to end up in the groundwater. And same thing here with river. Okay, and then it's not shown here is we can also have PFAS chemicals in the sediments. So the challenge is with the discharge of these chemicals is how they move in the environment, how they sorb, and whether they end up in the sediments where they can potentially be taken up by organisms. We also use sorbents in engineered systems. Mike talked about this with regard to the PFAS chemicals and how they are using organic carbon. They're specifically using granular activated carbon, shown here, to remove PFAS chemicals from the waste stream, as he discussed. Talk a little bit more about that. We can also use metal oxides, and shown here is an iron oxide, and that can be used for adsorbing naturally occurring organic matter. It can also be used for adsorbing cations and anions. So for example, alumina is a metal oxide and can be used for adsorbing arsenic, which is actually present as arsenate or arsenite in waters. And then there's ion exchange resins, which again we will talk about. And here we're looking at removing either cations or anions. We don't remove neutral compounds with ion exchange. We're actually removing ionic species. In order to prepare chemicals for use as sorbents, they have to be treated. So in order to treat the activated carbon, we can take coal, we can take wood. Work's been done in cherry pits, especially in Michigan because of the cherry industry. There's a significant amount of cherry pits. That material is then heated in the absence of oxygen to form graphitic char. That's the process called pyrolysis. And then the surfaces of that site, those sites need to be activated. So this graphitic char is then exposed to air or steam. That results in partial oxidation and the formation of oxygen-containing surface groups and these very, very tiny pores. So what we're actually trying to do, so this is our grain of activated carbon. What we want to do is we want to produce a sorbent that has a significant amount of pores. So it's a very, very porous structure with very high surface area. So not uncommon. We're talking about surface areas on the order of 500 to 1,000 square meters per gram of sorbent material. The vast majority of the surface areas are these micropore structure. Now, one thing to recognize is that adsorption is exothermic, which means what? If something is exothermic, what does that mean?
It produces heat.
Okay, it produces heat, so it's giving off heat. So if this is our sorbent, and let's do PCBs, okay, and what we're looking at is sorbing those PCBs, that's going to give off heat. So how does temperature affect sorption processes? If I raise the temperature, what happens? If it's giving off heat and I raise the temperature, which way will that shift the equilibrium? It's going to shift it to the left. So if I increase temperature, I decrease the capacity. I actually increase the rate because the rate is typically diffusion limited. So if I increase the rate of diffusion, I can increase the rate of reaction, but I will decrease the capacity. The starting material also plays a significant role. Mike mentioned this when he talked about the PFAS chemicals, when he mentioned that the carbon that they used was coal-based, and they had found that that was the most efficient carbon, granular activated carbon, for PFAS removal. So the starting material plays an important role in the efficiency. The pore size and distribution, that internal surface area is extremely important. Most of the sorption occurs in the internal surface area. So the more surface area, theoretically, the greater the capacity. And activation plays a significant role in the surface chemistry, and that plays a significant role in the efficiency. Lastly, the particle size affects it. So we typically talk about granular activated carbon and powdered activated carbon. Powdered activated carbon is kind of the consistency of just like talcum powder, the powder that you would use. And on the other hand, granular activated carbon is kind of the consistency size of salt, maybe a little bit bigger than that. Okay. The extent for the same type of carbon, the extent of the sorption, so if we have the same type, the extent of sorption is the same. The rate is greatest in the powdered activated carbon. And that's simply because if this is our particles, we have a stagnant layer, water layer around that, and the chemical has to diffuse through that. We just have more surface area for the same amount of carbon. So the rate increases, but the extent of sorption does not. And you can see that in this figure here, where we're looking at, we have the bulk solution out here. These are our molecules, so we'll look at these as copper ions from that first. We have a stagnant layer surrounding our particle. So those copper ions have to diffuse through that stagnant layer. They then have to diffuse into the micropore. So you can see that here. And what this attempts to show is that at equilibrium, we have these, in this case, we'll think of these as copper ions. The copper ions sorbed to the solid surface, and the open circles are the copper ions that are still in solution. So we can think about this now as an example where in this case we have 100 milligrams per liter of total organic carbon. We add 2 liters of that solution into 4 beakers. So this is typically how we would do what we refer to as an isotherm experiment. It's iso, same therm temperature. So we want to do these at the same temperature. So we've got these 2 liters of solution containing 100 milligrams per liter. So this is our initial concentration. In the first one, we'll add 3 grams of activated carbon, 5 grams in the second, 7 grams in the third, and 0, our control, in the fourth. So we're going to mix and we'll allow the system to come to equilibrium. When it's come to equilibrium, and typically what we do is we do a kinetic experiment first to determine how long it takes to reach equilibrium. We then determine the concentration at equilibrium. So these are the equilibrium concentrations. And we can determine then the mass of TOC that is adsorbed per mass of carbon. So for example, if we start at this 100 milligrams per liter, and we have 2 liters, so that means the mass initially is 200 milligrams. So the mass adsorbed per mass of adsorbent is equal to 200 minus 50 over, actually, the C equilibrium is 50 milligrams per liter times 2 liters. So that's 100 milligrams. So that is 100 milligrams divided by 3 grams, and that is 33.3 milligrams of TOC absorbed per gram of granular activated carbon. So that gives us the mass adsorbed. And we could do the same sets of calculations for both the 5 and the 7 gram solutions. And what we would end up with is a graph that actually would look something like this if we plot what is referred to as X over M, the mass of sorbate divided by the grams of sorbent divided by the equilibrium concentration. If we plot this data, we would end up with a graph like that. We typically model these systems by what are referred to as isotherm models. There are a number of isotherm models. I will only talk about a few of these. There are probably 10 or so different types of isotherm models that you can use. The Freundlich isotherm is entirely empirical, and what it states is that the X over M value is a function of the equilibrium concentration to the 1 over N power. So this is entirely empirical. And we can linearize that by taking either the natural log or the log base 10 of X over M. That equals 1 divided by N times the natural log of the equilibrium concentration plus ln of K. Okay, so this is our y-intercept, and this is our slope. So we're plotting ln X over M versus ln of the equilibrium concentration. The Langmuir isotherm, which we'll talk a little bit more about, is actually thermodynamically derived. So it has some basis in thermodynamics. Here, we linearize it by plotting 1 over X over M versus 1 over C sub B. That's how we linearize the Langmuir. And then we have what's referred to as linear isotherms. These are for much lower concentrations, and these are typically used with soil or sediment systems. And here, for instance, what you're looking at is the concentration of the chemical in the organic component of the soil. So you can see it's actually micrograms sorbed instead of milligrams, it's micrograms, 1,000-fold less per kilogram of soil organic matter. So you're really looking at that soil organic fraction. We also talk about soil water partition coefficients, and here now you're looking at the actual concentration in the soil itself, so the bulk soil. And that is related to this KOC value as a function of the fraction of organic matter. We also talk about octanol water partition coefficients. And here you're looking at what we refer to as KOWs, and these are the concentration of your contaminant in octanol divided by the concentration in water. And we use that to try and predict the concentration of a chemical in cellular material, especially in fatty tissue, because that's often where organics accumulate in an organism. And then sometimes we will also talk about bioconcentration factors. And here we're looking at the accumulation of these organics in an organism. And this is the concentration in the organism divided by the concentration in water. So for instance, we're looking at the concentration of PFAS chemicals in fish. So we're looking at how much does that organism accumulate these chemicals. So as I mentioned, the Langmuir isotherm is thermodynamically derived. And this A term here is related to the mass required to achieve monolayer coverage. If you think about these sorbents that we talked about, much of it is actually going to be in the porous structure. What you're thinking about is how much chemical can actually sorb, and you only have one layer. You don't have the adsorption, for instance, or the accumulation of multiple layers of chemical. This K is actually thermodynamically derived. So if we think of this as a vacant site on the sorbent that can react, that reacts with your chemical to produce a surface complex. This K is the equilibrium between the surface complex, the vacant site, and the chemical in solution. So it's truly thermodynamically derived. So we assume here that chemicals can only attach on a monolayer coverage. We have a limited availability of surface sites, that adsorption is reversible, that we reach equilibrium, and that, for instance, one site, so the sorption of, let's say, copper here, doesn't affect absorption at an adjacent site. So that's the basis for the Langmuir isotherm. And you can see here we've got some data plotted where we're plotting this X/M ratio versus the equilibrium concentration. And as I mentioned, we linearize this by taking the inverse of the concentration and the inverse of X/M. We plot that. The y-intercept is 1/A, and the slope is 1/A times K. So from that, we can determine both of these parameters. So we can see that as well here. we have the Freundlich isotherm. So this is, as I mentioned, totally empirical. We're plotting X over M versus the equilibrium concentration. And we describe the relationship with a power function. We linearize this by taking either the natural log or the log base 10. And log of k is our y-intercept. And 1 over n is the slope. And what you can see here, for instance, at log equilibrium concentrations greater than about 0, okay, that this carbon is the best. If your equilibrium concentrations are less, then this carbon is the best. And in no case, except maybe if we went to very, very high concentrations, would this carbon be the optimal. So we can use this to try and do empirical studies, determine these parameters, model the adsorption, and then what we will do is we'll use this information in the design of these systems. So we can do an example here where now what we have is we have the situation where we've got 6 flasks. Each of them contains 200 milliliters of a solution that contains benzene at 250 milligrams per liter. We have an additional flask shown here that contains benzene but no carbon. So this is our control or our blank. And you're asked then to take this data and analyze it so that you can plot the Freundlich and Langmuir isotherm. So looking at the data here, we start with a volume of 200 milliliters, and C naught is 250 milligrams per liter. So looking at the first flask, we have 0.2 liters times, we start with 250 milligrams per liter. We have 4.7 milligrams per liter, and that is 49.06 milligrams that has sorbed. So this is the mass of benzene that is sorbed. So if we take 49.06 divided by 0.804 grams, so this is milligrams, this is grams, that is 61.02 milligrams of benzene per gram of activated carbon. We can do the same sets of calculations for the others. So for instance, here we have 0.2 times 250 minus 7. And this is liters, this is milligrams per liter. We'll divide that by 0.668 grams, and that is 72.75 milligrams of benzene per gram of activated carbon. Similar sets of calculations here, and we would have 94.02, and that's milligrams per gram. And we have that here. So we can plot X over M versus C sub V. We have a nonlinear plot. We can then plot in this case, it's the natural log of X over M versus the natural log of the equilibrium concentration. Notice we have a straight line here. So we've linearized the data. We now have an equation. We've got an R squared, and we can determine the log of K is our y-intercept here. And we take then 10 to the 1.57, and that gives us K. The slope is the 1 over n, so this is our 1 over n. And we can write an equilibrium expression. So this is the Freundlich isotherm for the data that we obtained. We can do the same for a Langmuir isotherm. Again, we're linearizing the data, in this case by 1 over X over M versus 1 over the concentration. This is our Langmuir isotherm. So we linearized it in this way here. And we have an equation for a line. So this is 1 over AK. This is 1 over A. This is 1 over X over M. This is 1 over C sub E. So we determine 1 over A. We can determine A. 1 over A times K. So we have K. And we can determine then a Langmuir isotherm. So we'll end there. Happy to answer any questions. And on Wednesday, we'll start some examples looking at how to apply this in an engineered system. Any questions?